Did you know that the entire written history of humankind, from the first Sumerian cuneiform to the text message you sent today, spans roughly 5,000 years? Now, hold that number in your mind. 5,000. The supercontinent of Pangea broke apart around 175 million years ago. That means you could fit the whole of our recorded story into that expanse of time, not once, not 100 times, but 35,000 times over. Our entire civilization is a flicker in the long night of geologic time. It's a scale that defies easy comprehension, and it opens a quiet, persistent question. In all that unimaginable time before us, was there anyone else? Hello, and welcome. If you're here to fall asleep, you're in the perfect place. Let the story wash over you. There's no test at the end. I love seeing where everyone is listening from, so if you feel like it, leave a comment with your city and what time it is there. It's a wonderful way to feel connected across the globe. Tonight, we are going on a journey to a world that existed long before our own, a world where all the lands were one. We are going to Pangea, and we are going to ask, could an intelligent civilization have called it home? Let's begin not with a map, but with a feeling. Imagine you are standing on a shoreline. The air is thick, heavier with oxygen than the air you breathe now, and it carries an unfamiliar, earthy scent. There are no flowers, so there is no sweetness on the breeze. Instead, there is the smell of damp soil, of giant ferns releasing their spores, and the resinous tang of early conifers. The sun feels different, somehow older, casting a light that seems filtered through a different quality of atmosphere. You look out at the water, a great expanse of sea called the Tethys. To your left, the coast stretches north. To your right, it curves south. Now, here is the turn. The land you are standing on will one day be called North America, and if you could walk for weeks and weeks to the south, you would cross onto the continent we now know as South America. If you were to turn around and walk east, away from the Tethys Sea, you would not find an ocean. Instead, you would walk across plains, river valleys, and eventually mountains, until you found yourself in what would, after hundreds of millions of years, become Africa and Europe. This was Pangea. The name means all lands, and for a time, from the late Carboniferous through the Jurassic, it was nearly true. Assembled by the early Permian period, around 299 million years ago, it was a single, colossal landmass. It was surrounded by a truly global ocean, a world of water known as Panthalassa, meaning all seas. To the east of this supercontinent, cupped in its giant C shape, lay the Tethys Sea. This body of water separated the northern part, Laurasia, from the southern part, Gondwana. It was a warm, tropical sea that served as a cradle for marine life, a kind of evolutionary nursery whose biological legacy would eventually spread into the new oceans of the world. Through the slow dance of geology, its gradual closing would give rise to the mountain ranges of the Alps and Himalayas, but in this ancient time, it was a wide, open waterway. The United States Geological Survey gives us a picture of this arrangement. From about 300 to 200 million years ago, the familiar shapes of our world were locked together in an unfamiliar embrace. The eastern coast of North America was pressed firmly against the western coast of Africa. There was no Atlantic Ocean. It simply did not exist. The great rifting, the tearing apart of this world, only began when immense plumes of magma from deep within the earth welled up, pushing and breaking the crust between Africa, South America, and North America. It was a process of continental separation so slow it would be imperceptible to any being living through it, yet so powerful it would define the next 200 million years of our planet's history. It was the planet itself breathing, in and out, on a timescale of eons. And this brings us to our central inquiry. In that immense stretch of time, could an intelligent species have risen, built a society, and vanished? Mainstream science is clear. There is no evidence for any pre-human industrial civilization. But the question itself is not unscientific. In fact, it has a name. The Silurian hypothesis, proposed in a 2018 paper by astrophysicist Adam Frank and climatologist Gavin Schmidt, doesn't claim a civilization existed. Instead, it asks a more practical question. If one had existed, what kind of evidence would it leave behind? How would we even know? Would it be fossilized ruins? Or would the traces be more subtle? They suggest we should look for things like unusual spikes in carbon isotopes from mass fossil fuel burning, or perhaps synthetic chemical compounds that don't occur in nature, or even the remnants of plastics in ancient sediment. Could such a signature, a kind of planetary scar, survive for tens or hundreds of millions of years? This thought experiment is more than just a flight of fancy. It helps scientists refine their methods for searching for life on other planets. If we can't find evidence of an industrial civilization on our own world, what does that say about how we should search for them on Mars or worlds orbiting other stars? It forces us to think critically about what evidence even means over geologic timescales. To appreciate the scale we are dealing with, consider our own species. Anatomically modern Homo sapiens, people who look like us, appeared around 300,000 years ago, based on fossils found at a site in Morocco called Jebel Irhoud. 300,000 years. Pangea began breaking apart 175 million years ago. This means our species is nearly 600 times younger than the era of Pangea's final days. We are far too recent to have ever walked its shores. So, if there was a civilization, it wasn't ours. It would have belonged to someone else entirely. A species that rose, flourished, and fell in a world we can now only reconstruct from silent rock. The sheer depth of time is a character in this story. It is an ocean of years so vast that entire worlds of life could rise and fall within it, leaving behind only the faintest of ripples. In our journey tonight, we will explore this possibility. We will tour the real, known geology of Pangea, grounding ourselves in what the stones tell us. And we will also engage in thoughtful speculation, exploring the what-ifs while always labeling them as such. Our guiding principle is simple: wonder is always welcome. But extraordinary claims require extraordinary evidence. We will look for that evidence, or its absence, in the peer-reviewed work of geologists and paleontologists, and in the findings of the world's major scientific institutions. For now, just stay with that image. Standing on a Pangean shore, where continents connect without an ocean between them. The world is one. And in that oneness, we begin our search. The story is just getting started. Let's try to see this ancient world more clearly, to paint a picture of its geography, not with a brush, but with the data pulled from the rocks themselves. Pangea was not just a blob of land. It had a distinct shape and character. Picture it. Again, a massive C shape, with the bulk of its mass centered near the equator. This position had profound consequences for its climate, creating conditions unlike almost anything on Earth today. The open part of the sea held the warm, Tethys Sea, a kind of enormous tropical gulf. This sea was a realm of marine life, and its currents would have brought moisture and warmth to the coastlines that bordered it. Over eons, as the continents drifted, the slow closing of the Tethys would eventually form the mountain ranges of the Alps and the Himalayas. But back then, it was a wide, open waterway providing a stable, life-friendly margin to an otherwise harsh continent. The very creation of Pangea left its mark on the land. When continents collide, they don't just meet, they crumple. The incredible pressures raise colossal mountain ranges. We can still see the roots of these Pangean mountains today. The Appalachian Mountains in North America and the Variscan and Hercynian belts in Europe are, in fact, parts of the same gigantic chain. They were once a single unified system known as the Central Pangean Mountains, a continental spine running through the heart of the supercontinent. Imagine a mountain range as continuous as the Rockies, but stretching from what is now Texas through the eastern United States, across Greenland and into Poland. These were not young, sharp peaks like the Himalayas of today. By the time of Pangea, they were already ancient and eroding, worn down by millions of years of wind and rain. They would have functioned as a massive weather barrier, blocking moisture from the Tethys and Panthalassa from reaching the deep interior, thus creating a pronounced rain shadow that made the continent's center even more arid. While the coasts might have been temperate, the interior of this superworld was a place of extremes. Its sheer size created a climate dominated by what scientists call megamonsoons. Because the landmass was so enormous, the central regions were far from the moderating influence of any ocean. This led to brutally hot, dry seasons that would last for many months. Picture a landscape of cracked red earth, vast salt flats, and sand dunes under a relentless sun. Many animals would have survived by estivating, entering a state of dormancy in deep burrows to wait out the heat and drought. Then, as the seasonal patterns of atmospheric pressure shifted, the weather would change with incredible force. Warm, moist air from the surrounding Panthalassan Ocean would be pulled inland. The change would begin subtly, a shift in the wind, a gathering of clouds on the distant horizon, the first scent of rain on dry earth, a planetary-scale petrichor. This would build into torrential rains that could last for months on end. These were not simple summer showers. They were continental-scale deluges that would cause immense flooding, filling the dry basins and carving temporary violent rivers into the land. Life in the Pangean interior would have been a story of extreme endurance, of waiting for the water to come, and then surviving its overwhelming arrival. We know these continents were connected not just from the shape of their coastlines, but from the silent testimony of the fossils they share. Consider the Mesosaurus, a small freshwater reptile about a meter long. Its fossils are found in just 2 places on Earth, in certain rock formations in South America and in southern Africa. Mesosaurus was a creature of lakes and rivers. It was not equipped to cross a vast saltwater ocean. Its presence on both continents is undeniable proof that, at one time, those lands were joined. There was no Atlantic Ocean to cross. Then there is the Glossopteris, a type of seed fern that formed the dominant forests of its time. Its fossilized leaves are found across South America, Africa, India, Australia, and even Antarctica. This plant became a classic piece of evidence for the southern portion of Pangea, known as Gondwana. The seeds of Glossopteris were heavy and not suited for traveling across thousands of kilometers of open ocean. The only way it could have spread so widely is if these continents were locked together, allowing these great forests to colonize a single, continuous territory. Perhaps the most compelling traveler was Lystrosaurus. This creature was a synapsid, an early relative of mammals, about the size of a pig. It was a stout, hardy herbivore with a beaked face and 2 tusks. It lived during the early Triassic, just after the planet's most devastating mass extinction, and its ability to burrow may have been the key to its survival. Fossils of Lystrosaurus are found in what is now Antarctica, India, and South Africa. Its widespread distribution across southern Pangea shows that there were clear, unobstructed land routes connecting these distant locations. An animal could simply walk from what would become Africa to the land that would become Antarctica. Now, let us engage in a moment of clearly labelled speculation. If an intelligent species had arisen on Pangea, this single landmass would have offered an unprecedented opportunity for movement and exchange. There were no oceans to cross, no need to invent seafaring vessels for global travel. In theory, a caravan could travel overland from one pole to the other. However, the journey would not have been easy. The formidable, eroding stumps of the Central Pangean mountains would have still been a significant barrier, and the great central deserts, with their extreme heat and seasonal droughts followed by massive floods, would have been almost impassable for much of the year. Any civilization would have likely grown along the more temperate coasts of the Tethys Sea, or followed the great river systems fed by the monsoons. The continents were connected, but they were not without their borders. The real maps of this world would have been drawn not by oceans but by mountains, deserts, and the life-giving and life-taking patterns of the rain. When we look for signs of a lost world, our minds are naturally drawn to patterns. We search for order in the chaos, for shapes that seem too perfect, too symmetrical to be the work of chance. And our planet is full of such geologic curiosities, places that whisper of forgotten histories and challenge our sense of what is natural and what is made. But the Earth itself is a powerful architect, a sculptor working with stone and time, capable of creating structures of breathtaking precision. Let's look at a few of these natural wonders that are sometimes mistaken for the ruins of a bygone age. Fly with me in your mind to the nation of Mauritania, in West Africa. We are high above the Sahara Desert. Below us, a remarkable feature dominates the sandy expanse. It is a circular structure, a series of concentric rings 40 to 45 kilometers across. It looks like a giant bullseye, or the iris of an eye staring up at the sky. This is the Richet structure, often called the Eye of the Sahara. It is so distinct that it became a visual landmark for astronauts on early space missions, a familiar anchor in the uniform sea of sand. For a time, scientists thought it might be an ancient impact crater. Its near-perfect symmetry seemed to suggest a singular, catastrophic event. Some have even speculated that it could be the location of Plato's lost city of Atlantis, with its described concentric rings of land and water. However, detailed geological study tells a different story. According to the NASA Earth Observatory, the Richet structure is not an impact crater. It is what geologists call a domed anticline. Imagine a deep layer of rock being pushed up from below by magma that never reached the surface, creating a large blister-like dome. Over millions of years, the top of this dome eroded away, exposing the layers of rock beneath, like the skin of an onion being peeled. The rings we see today are the edges of these different rock layers, some harder and more resistant to erosion than others. It is a completely natural formation, a beautiful dissection of a geologic dome. It is magnificent, but it is not a city. Let's travel now to the warm, clear waters of the Bahamas. Just off the coast of the island of Bimini, under a few meters of water, lies a formation known as the Bimini Road. It is a submerged line of large, rectangular limestone blocks, arranged in a way that looks very much like a paved road or the foundation of a wall. It is easy to see why many believe it to be a man-made structure, perhaps a remnant of a civilization swallowed by the sea. Yet, once again, geology offers a more prosaic, though equally fascinating, explanation. The consensus among geologists and archaeologists is that the Bimini Road is a natural feature made of beach rock. Beach rock forms in tropical and subtropical intertidal zones when sand and shells are cemented together by calcium carbonate precipitating from seawater. This process can create large, flat slabs of oolitic limestone, which is essentially made of tiny carbonate pearls bonded together. Over time, as the slabs are subjected to stress from subsidence or sea level changes, they can fracture along straight, parallel lines, a process called jointing. The result is a collection of blocky, rectangular shapes that look for all the world like cut stone masonry. The late United States Geological Survey geologist Eugene Shin studied the formation extensively, concluding in publications like Skeptical Inquirer that its origin was entirely natural. There are no tool marks, no mortar, and the stones are composed of the same material as the nearby shoreline. Our final stop is in South Africa, in pyrophyllite mines near the town of Klerksdorp. Here, miners have found small, spherical or disc-shaped objects, often with parallel grooves around their circumference. These Klerksdorp spheres, found in deposits nearly 3 billion years old, have become famous as potential out-of-place artifacts. They look manufactured, but detailed petrographic analysis, the study of rocks under a microscope, reveals their true nature. They are natural concretions. Concretions form when minerals in groundwater precipitate around a nucleus, like a grain of sand or a tiny fossil fragment, within a deposit of sediment. As more and more mineral layers are added, the object grows, often into a remarkably symmetrical shape. The grooves are simply a result of the fine-grained laminations in the surrounding sediment being imprinted on the concretion's surface as it formed. We see this same process create other strange shapes all over the world, like the massive cannonball-like concretions found in North Dakota. Nature, it seems, is very good at making spheres. What is the takeaway from these journeys? It is that symmetry, alignment, or blocky shapes are not, by themselves, proof of engineering. Geology is filled with processes that create stunning patterns. The human mind is wired for pattern recognition. It is a survival trait. But it can lead us to see intention where there is only physics and chemistry. To argue for an artificial origin, one needs a higher standard of proof. Are there tool marks? Are the materials something that doesn't occur naturally in that location? Is the object found in a context with other cultural traces, like pottery or waste materials? For these, famous mysteries and many others, the answer is no. This doesn't diminish their wonder. It invites us into a deeper form of enchantment, not the magic of a lost civilization, but the intricate and beautiful magic of our planet's own slow, creative processes. How do we know anything about a world that existed millions of years ago? The answer is written in the Earth's layers, in a language of stone and bone. Paleontologists read this language through a slow, meticulous process. They date rocks using radiometric methods. Think of it like a perfect hourglass. When a volcanic rock crystallizes from magma, certain radioactive isotopes, like uranium, are locked into its crystal structure. These parent isotopes begin to decay into stable daughter isotopes like lead at a precise, unchangeable rate. It's like flipping the hourglass. By carefully measuring the ratio of parent to daughter isotopes in a crystal, scientists can calculate exactly how much time has passed since that rock cooled and solidified, providing an atomic clock that ticks away over eons. This is then combined with relative stratigraphy, the simple but powerful idea that in an undisturbed sequence of rocks, the deeper layers are older than the ones on top. This work is cumulative, built piece by piece from countless field sites around the globe. Context is everything. A single bone is a curiosity. A bone found in a specific layer, alongside other known fossils, becomes a piece of data, a word in a sentence about the ancient past. But this geologic library is profoundly incomplete. The fossil record is a book with most of its pages missing, and most of the letters faded from the pages that remain. Fossilization is an incredibly rare event. Let's follow the journey of a single Lystrosaurus bone. The animal dies near a river. A scavenger doesn't find its carcass. A seasonal flood quickly buries it under a thick layer of silt, cutting it off from the decaying effects of oxygen. Over thousands of years, more and more sediment piles on top, the pressure increasing. Over millions of years, groundwater, rich in dissolved minerals like silica or calcite, percolates through the porous bone. Molecule by molecule, the original organic material is replaced by these durable minerals, creating a perfect stone replica. This is just one of many ways a fossil can form, and every step is a lottery. Most living things simply die, decay, and vanish without a trace. The absence of fossils is not therefore absolute proof that something didn't exist, but it does mean that extraordinary claims require extraordinary evidence. The burden of proof lies with the discovery, not with the silence. There is even a scientific principle that describes this inherent incompleteness: the senior lips effect. It explains that because the fossil record is spotty, the first appearance of a species in the rocks is almost always later than when it truly originated, and its last appearance is almost always before it truly went extinct. Gaps are not the exception, they are the rule. We are always working with an imperfect picture, a story with a beginning and an end we can only estimate. It is this understanding of the Earth's processes that provides the most elegant explanation for one of the key pieces of evidence for Pangea. As we discussed, the discovery of identical, non-marine fossils on continents, now separated by vast oceans, was a major puzzle. Before the theory of plate tectonics was accepted, some proposed the existence of enormous sunken land bridges, or even lost continents to explain this. But the simplest explanation, supported by a mountain of other evidence, turned out to be the correct one. The continents themselves had moved. The animals didn't cross the oceans. The oceans formed between their homes after they were gone. The Earth's surface is not static. It is constantly being remade. The ocean floor, in particular, is continuously recycled. Think of the mid-ocean, ridges as giant wounds where the planet's inner heat bleeds out, creating new crust that pushes the plates apart. Far away, at subduction zones, the old, cold, dense oceanic crust is swallowed back down into the hot mantle, its history erased. This process is so efficient that the seafloor is, geologically speaking, very young. Most of it is less than 200 million years old. Any trace of a civilization that existed on the ocean floor in Pangean times would have been almost entirely destroyed by now, consumed by this planetary recycling system. So, if an industrial civilization had existed back then, what kind of fingerprints would we look for? We wouldn't just be searching for a fossilized building or a stone tool. We would be looking for geochemical signals. Imagine the impact our own civilization is having. We are changing the chemistry of the atmosphere, leaving a distinct spike of old carbon isotopes in the sediment from burning fossil fuels. We have created novel synthetic compounds, plastics, whose long, complex polymer chains are entirely unnatural and will be preserved in rock layers for millions of years. These are the kinds of durable techno-fossils a Pangean civilization might have left behind. Yet, when we examine rock cores from the Permian and Triassic periods, we find no such verified anomalies. There are no unusual concentrations of synthetic chemicals, no unexplained isotopic excursions that point to industrial activity. Compare this absence of evidence to the overwhelming presence of other forms of life. Bone beds of the creature. Lystrosaurus are so common in early Triassic rocks that they are used to define that period of geologic time. This one species fossilized so well and in such numbers that its existence is undeniable. Yet in all those same layers, we find no analogous techno-assemblages, no collections of manufactured objects, no quarries, no fossilized waste dumps. The rocks are full of the stories of life, but utterly silent on the story of technology. Humanity has always been captivated by the idea of lost worlds. Long before geology gave us a map of Pangea, our myths and legends were filled with stories of great civilizations that vanished beneath the waves or were swallowed by the earth. These tales speak to a deep part of us, a sense of loss, a warning against hubris, and a hope that something of the past might one day be rediscovered. They represent a kind of cultural nostalgia for a past that never was. Let's explore 3 of the most famous of these phantom continents: Atlantis, Lemuria, and Mu. The story of Atlantis is the oldest and most influential. It comes to us from the Greek philosopher Plato in his dialogues Timaeus and Critias, written around 360 before Common Era. Plato describes Atlantis as a great naval power located beyond the Pillars of Hercules, what we now call the Strait of Gibraltar. He paints a detailed picture of its capital city, with concentric rings of land and water, magnificent temples, and advanced engineering. He even mentions a mysterious metal, orichalcum, that shone like fire. Atlantis was an island continent of immense power and sophistication that, after a failed attempt to invade Athens, was submerged by the sea in a single day and night of misfortune. For most of classical history, Plato's account was understood as what he likely intended it to be: a philosophical allegory. It was a cautionary tale, using the fictional, hubristic empire of Atlantis as a foil to showcase the virtues of his own idealized philosophical Athens. It was a story about morality and politics, not a historical record. It was only in later centuries that people began to search for a real, physical Atlantis, taking the allegory as literal history. The story of Lemuria has a very different origin. It was not born from myth, but from 19th century science. In the 1860s, the zoologist Philip Sclater was puzzled by the distribution of lemurs. These primates were found in Madagascar, but their close relatives were also found in India and Southeast Asia. To explain this, without the benefit of plate tectonic theory, Sclater proposed that a massive continent had once existed in the Indian Ocean, connecting these lands. He named it Lemuria. In the scientific context of the time, this was a perfectly reasonable hypothesis. Scientists of the era proposed many land bridges to explain the strange distributions of plants and animals around the world. However, as our understanding of geology grew, the theory of plate tectonics provided a much better and more comprehensive explanation. The idea of Lemuria was superseded and abandoned by the scientific community, yet the name and the concept took on a new life, migrating from a discarded scientific hypothesis into the world of the occult and theosophy, where it was reimagined as the mystical homeland of an ancient, spiritually advanced race. Lemuria illustrates how an idea can outlive its evidence, transforming from a scientific model into a cultural myth. The third lost continent, Mu, is a more modern creation. It was popularized in the 1920s by a writer named James Churchward, who claimed to have translated ancient texts from a Himalayan monastery that told the story of a vast continent in the Pacific Ocean. According to Churchward, Mu was the cradle of all human civilization, and it sank into the sea tens of thousands of years ago, leaving behind only the scattered islands of Polynesia as its peaks. Geologists, however, have completely rejected the notion of Mu. The floor of the Pacific Ocean is made of dense oceanic crust, not the lighter continental crust a landmass of that size would require. It shows no evidence of a sunken continent, and the idea of a landmass of that size disappearing so quickly is physically implausible according to everything we know about the Earth's crust. What do these stories have to do with Pangea? They are culturally important, but chronologically, they exist in a completely different universe. To compare the age of Plato's story to the age of Pangea is like comparing the length of a single human breath to the entire recorded history of a mountain, a range. These myths are human stories, products of our own history, our own science, and our own imagination. If any myth were to contain a genuine echo of a Pangean reality, the chain of transmission would be unimaginably long. A story would have to be passed down through countless generations, surviving mass extinctions and the complete rearrangement of the planet's continents for over 300 million years. This is beyond any plausible timescale for human oral or written tradition. There is a fascinating field of study called geomythology, which looks for real geological events encoded in ancient myths. But this field treats myths as clues to investigate recent events, like the eruption of a volcano a few thousand years ago, not as literal proof of deep-time civilizations. These stories are powerful. They shape our sense of identity and our place in the cosmos, but they must be separated from the geological evidence. We can appreciate Atlantis as a brilliant philosophical fable without needing it to be a physical place. By placing these stories on a timeline, we can see them for what they are, reflections not of a lost geologic world, but of the enduring, human need to make sense of the past and to imagine what might lie beyond the edges of our known maps. How do we responsibly explore an idea as profound as a lost civilization? We do it by using the right tools. The process of science is not about having all the answers. It is about having a reliable method for asking questions. Scientists and historians build hypotheses from patterns they observe, but that is only the first step. The crucial part is then testing those hypotheses against real-world data, field observations, laboratory analyses, and independent lines of evidence that all need to point in the same direction. It is like a detective solving a case. One clue is interesting, but a solid conclusion requires a web of evidence, fingerprints, motive, witness statements, all pointing to the same suspect. The Silurian hypothesis is a perfect example of this process in action. It doesn't just ask, what if? It asks, if so, then what? It provides a checklist of testable predictions. If an industrial civilization existed in deep time, we should look for specific signals in the rock record. For example, the burning of fossil fuels releases enormous amounts of carbon into the atmosphere. This carbon comes from ancient plants, which have a slightly different isotopic signature than the carbon actively cycling in the atmosphere. A massive release of this old carbon would leave a distinct chemical fingerprint in sedimentary rocks. Another signal would be synthetic molecules. The long polymer chains of plastics, for instance, are completely alien to nature. Their preservation in sediment would be an unambiguous sign of technology. We would also search for unusual spikes. In metals associated with industrial processes like cadmium, lead, and mercury that can't be explained by volcanic activity, this gives us a concrete search program. We are no longer just waving our hands, we are looking for specific fingerprints. We have a perfect analogue for this, our own era, the Anthropocene. The changes we are making to the planet will be detectable in the geologic record for millions of years. Future geologists will see a thin layer containing plastic microparticles, spherical fly ash from coal-fired power plants, and a unique radioactive signature from mid-20th century weapons testing. This is the kind of layer we should be looking for in older rocks. So far, we haven't found one. A key principle in this kind of investigation is Occam's razor, the idea that the simplest explanation that fits all the available facts is most likely the correct one. Plate tectonics is a far simpler and more powerful explanation for the distribution of fossils than inventing entire sunken continents. The natural process of erosion is a simpler explanation for the reshift structure than a lost city. This principle doesn't forbid complex explanations, but it demands that we rule out the simple, natural ones first. When we investigate mysteries, we must also be aware of the hazards of our own psychology. We are pattern-seeking creatures. Sometimes we fall victim to confirmation bias, where we favor information that supports our existing beliefs and ignore evidence that contradicts them. We can also experience apophenia, the tendency to see meaningful patterns in random noise. This is why the scientific method is so important. It uses tools like blind tests, statistical analysis, and demands that results be reproducible by other researchers, acting as a crucial check against our innate biases. Let's return to the Klerksdorp spheres. At first glance, they seem to defy natural explanation. But when we apply the tools of microscopy and mineralogy, the mystery dissolves. We see that their structure is consistent with the known natural process of concretion. The initial speculation gives way to a clear, evidence-based explanation. This is a case study in the importance of careful checking and applying the right tools. Dating also matters enormously. Modern geochronology, using methods like uranium lead dating on zircon crystals, can pinpoint the age of a rock layer with incredible precision, sometimes to within less than plus or minus 0.1 to 0.2 million years. This precision is critical. It has allowed scientists to demonstrate, for example, that the end Permian mass extinction happened at exactly the same time as the massive volcanic eruptions of the Siberian traps. This chronological link is the smoking gun evidence for what caused the extinction. Any proposed artifact from a Pangean civilization would need to be dated just as rigorously to ensure it truly belongs to that ancient world. There is a vital distinction between speculative fiction and science. Imagination is essential. It is where new ideas and hypotheses are born. But science requires that imagination be disciplined by data. We can let our minds wander and suggest new tests to run, new places to look, but in the end, we must let the evidence decide. An extraordinary claim, like a lost civilization, can be visualized as moving along a decision tree. It starts with a curiosity. That leads to fieldwork to gather data. The data is then subjected to laboratory testing. The results are submitted for peer review, where other experts try to find flaws in the argument. Only after clearing all these hurdles can a claim be accepted. The Pangean civilization hypothesis remains for now at the very first stage, a fascinating and worthwhile question. For this next part of our journey, we are going to step away from the hard evidence and into the realm of pure, thoughtful speculation. Let me be very clear. Everything that follows is a work of imagination, an exercise in thinking through the what-ifs. We are using the known facts about Pangea's environment as a foundation to build a hypothetical world. Let us imagine for a moment that such a civilization did exist. What might it have been like? Given the geography of Pangea, its inhabitants would likely have been a coastal people. The vast, arid interior, with its brutal mega-monsoons, would have been inhospitable for large permanent settlements. Their cities and towns might have lined the shores of the Tethys Sea and the great Panthalassan Ocean, taking advantage of the more stable climate and the abundant resources of the sea. Rivers, swollen by the seasonal rains, would have been lifelines, creating fertile floodplains that could have supported some form of agriculture. Perhaps their society would have been split. Settled, urban populations along the coasts, and nomadic groups in the interior who followed the rains and the seasonal migrations of animals. What would they have built with? Without evidence of large-scale smelting, their architecture would have been dominated by the materials at hand: stone, fired clay, and timber from the great fern and conifer forests. Stone structures might have survived, but anything made of wood would have long since decayed. Their buildings would have been low-rise, sprawling in patterns that followed the availability of water and resources, perhaps built with a deep understanding of natural ventilation to survive the heat. The idea of towering skyscrapers feels out of place. Their connection to the land would have been more direct, their structures built to withstand the extremes of the Pangean climate. Their science and technology might have evolved along a different path from our own. Without easily accessible metals, perhaps they became masters of stonework, biology, or chemistry. They might have developed sophisticated methods of agriculture to cope with the extreme seasons, or learned to create incredibly durable ceramics or glasses. Their energy sources might have been geothermal, tapping into the heat of a geologically active world, or solar, using the intense equatorial sun. What would their culture and belief systems have been like? They would have been shaped by their unique world. Their gods might have been gods of the sun and the rain, their myths tied to the punishing rhythm of the mega-monsoon cycle. The great mountain spine of Pangea could have been seen as the backbone of the world, a sacred place. Their understanding of the cosmos would have been different too. Because of the slow wobble of the Earth's axis, known as precession, and the movement of the continent itself, the constellations in their night sky would have been entirely different from ours. They would have navigated by different stars. Perhaps they would have been keenly aware of the planet's instability. Living in a world that had recently experienced the Great Dying, the end Permian extinction, might have embedded a deep-seated awareness of impermanence into their philosophy. Their greatest myths could have been stories of that earlier, catastrophic collapse, a warning from a forgotten time. What are the technological signals we would look for from such a society as, the Silurian hypothesis suggests, the most durable traces would be chemical? We'd scan ancient ice cores, if any could be found, or sedimentary layers for unusual spikes in carbon dioxide, nitrogen isotopes, or heavy metals that signal industrial processes. We might even search for synthetic polymers, ancient plastics that could not be produced by nature. If they had reached the stage of radio communication, the most likely place to find their mark would not be on Earth. Our planet's active geology is too efficient at erasing history. A better place to look would be for an artifact left on a stable, geologically dead surface, like our Moon or Mars. A single probe or monument left on the Moon would outlast any city built on Earth, if they were advanced enough to know their world was doomed. Perhaps that is where they would have left their final message, a bottle thrown into the cosmic ocean. Again, this is all a portrait of a phantom. In the actual rock record of Pangea, we find no evidence of any of this. No quarries, no fossilized fields, no unusual metal deposits, no synthetic molecules, and no monuments on the Moon. This exercise, in imagination, serves a purpose. It clarifies what we should be looking for if the idea were true. It gives us a search image. The story of this imagined civilization is compelling, but for now, it is a story we tell ourselves, not one the Earth has told us. The rocks remain silent on this matter, and their silence is, in its own way, an answer. If a civilization had managed to rise on Pangea, what could have possibly erased it so completely? To answer that, we must look at the immense, destructive forces that our planet can unleash. Earth's history is punctuated by catastrophes on a scale that can reset the course of life itself. These events don't just topple civilizations, they can rework the surface of the planet, burying or destroying almost everything that came before. The mechanisms of erasure are as powerful as the mechanisms of creation. Let us travel back to the end of the Permian period, around 252 million years ago. This was the time of Earth's most severe mass extinction, an event so devastating it is often called the Great Dying. Over 90% of marine species and 70% of terrestrial vertebrate species vanished. High-precision dating has linked this event directly to a cataclysmic episode of volcanism in what is now Siberia. This was not a single volcano. It was a large igneous province, or LIP, known as the Siberian Traps. For hundreds of thousands of years, colossal fissures in the Earth's crust poured out unbelievable volumes of lava, covering an area larger than Western Europe, in some places kilometers thick. Let's imagine the scene. The sky would have been dark with ash and sulfur aerosols, blocking out the sun and causing a volcanic winter. Acid rain would have stripped the land of vegetation. But the lava was only part of the story. As the magma surged through the Earth's crust, it baked huge underground deposits of coal and organic-rich shale, releasing immense quantities of greenhouse gases like carbon dioxide and methane into the atmosphere. This triggered runaway global warming. The oceans heated up and became acidic, dissolving the shells of marine organisms. The warmer water could not hold as much oxygen, and vast swathes of the ocean became anoxic, suffocating most life. The water may have even turned a ghastly purple, colored by anaerobic bacteria. An event like the Siberian Traps doesn't just cause an extinction, it is a continental-scale resurfacing. It could have easily buried any surface structures under kilometers of basalt and ash, while the resulting climate chaos would have wiped out the ecosystem that supported any advanced life. Then, as Pangea began to tear itself apart, another of these fiery catastrophes occurred. At the end of the Triassic period, around 201 million years ago, the Central Atlantic Magmatic Province, or CAMP, erupted. This was another, enormous large igneous province, this time associated with the rifting between Africa, Europe, and the Americas. Again, massive lava flows and gas releases are linked by high-precision dating directly to the major extinction event that closed the Triassic period. Imagine the ground itself shaking and splitting apart for millennia as a new ocean was violently born in a sea of fire. This was another civilization-ending and evidence-erasing event. And of course, there are threats from beyond our world. We know what happened 66 million years ago, at the end of the Cretaceous period. An asteroid or comet slammed into the planet at what is now the Yucatan Peninsula. The Chicxulub impact created a crater 180 kilometers across and unleashed energy equivalent to billions of atomic bombs. It created a global ejecta layer marked by the element iridium. This event was the primary cause of the extinction that wiped out the non-avian dinosaurs. These events show us how vulnerable life might be, but they also show us how the evidence itself gets wiped. Plate tectonics is the slow, relentless engine of erasure. Over hundreds of millions of years, continental plates move, mountains are pushed up and eroded down to their roots, and seabeds are subducted back into the mantle. Metamorphism, the process by which rocks are changed by heat and pressure, can distort and destroy any fossils or structures contained within them. Even ice can be an eraser. During later ice ages, massive glaciers, kilometers thick, acted like continental-scale bulldozers, scraping landscapes down to the bedrock and grinding any evidence from previous ages into dust. So, if a Pangean civilization had existed, there are many plausible ways it could have ended. The great volcanic provinces or a major impact are powerful candidates. These are not just civilization enders, they are evidence erasers. It is a sobering thought. The same planetary processes that create new worlds are also powerful enough to wipe the slate clean, leaving behind almost no trace of what came before. The very dynamism of our planet, the engine of its long and complex history, may also be the ultimate guardian of its deepest secrets. The story of a lost world might not be written in any surviving text, but in a layer of ash and a profound, planetary silence. So where does our journey leave us after traveling across the ancient continent, exploring its climate, its life, and its violent end? What can we say about the possibility of a lost civilization? The mainstream scientific position is, and must be, guided by the evidence. And, currently, there is no verified, credible evidence of any pre-human civilization in deep time. This conclusion isn't a dismissal of the question. It's a reflection of the data we have gathered from the rock record. It's an answer based on decades of meticulous fieldwork and laboratory analysis by thousands of scientists around the world. The Silurian hypothesis is so valuable because it moves the conversation from the realm of pure fantasy into the framework of science. It formalizes what would count as evidence. It gives us a set of tools and a search pattern. Instead of just looking for ruins, it tells us to look for subtle chemical traces, for the kind of planetary footprint that an industrial species would inevitably leave. It turns a vague idea into a series of testable hypotheses. This is how science makes progress on even the most profound questions. It's important to distinguish here between a mystery and a conspiracy. A mystery is an open question, an invitation to investigate with transparent methods. A conspiracy suggests evidence is being actively hidden or suppressed. Science thrives on solving mysteries. It has no room for unsubstantiated conspiracies. When we look at the Pangean rock record, what we find is rich and detailed. We have an incredible number of fossils that paint a picture of the ecosystems of the time. Yet this record is consistently devoid of anything that looks like technology or culture. The story it tells is one of natural history, of evolution and extinction driven by planetary forces. The absence of evidence is striking when compared to the abundance of other kinds of evidence. We have also seen how natural mysteries often have elegant geologic explanations. Understanding the natural processes behind these features doesn't make them less wondrous. It adds a new layer of appreciation for the creative power of our own planet. This is the beauty of the scientific process. It replaces simple supernatural explanations with deeper, more complex, and ultimately more satisfying natural ones. The great mythic narratives of Atlantis, Lemuria, and Mu are compelling stories. But they are human stories, from a human timescale. They do not substitute for empirical data from the geologic past. They are culturally significant, but they are not evidence for a civilization that would be hundreds of millions of years older than the stories themselves. The great power of science is its provisional nature. Scientific truth is not dogma. It is our best current explanation based on the available evidence. Conclusions can and do change when new, compelling evidence emerges. Our understanding of dinosaurs, for example, has changed dramatically over the past few decades, from slow grey lizards to active, dynamic, and often feathered animals. This is a sign of a healthy, self-correcting process, not a weakness. If a verified, pre-human artifact were discovered tomorrow, dated precisely to the Permian period, the consensus would be overturned. Science would not collapse, it would expand to incorporate this new, revolutionary piece of data. But the evidence would have to be extraordinary. As storytellers and explorers of the past, there is a responsibility to maintain the trust of the audience. That means being honest about the line between evidence and speculation. Public imagination plays a vital role in this process. Curiosity about lost worlds motivates exploration. It pushes us to develop new methods. But it must be paired with intellectual honesty. The bigger lesson in all of this is that the true, history of our Earth is vaster and, in many ways, stranger than any single story we could invent. It is a tale of continents in motion, of climates shifting from hothouse to ice age, of life rising and falling in great waves of creation and extinction. And the most amazing part is that this story is not lost. It has left legible marks, a faint handwriting on stone, that we are, generation by generation, learning how to read. Our credibility as explorers of this past depends on a simple rhythm: to welcome wonder, but to be guided by evidence. We must always clearly flag where speculation begins and where the data ends. Curiosity is the feature that drives us, the engine of our inquiry. It is how we learn what is truly there. And what is there is wonder enough. As we drift towards sleep, let the vastness of this story settle. Let the immense scales of time wash over you, not as a source of anxiety, but as a deep and calming rhythm. Pangea, the world of all lands, was not a permanent state. It was a chapter. It assembled in the deep past of the Permian, and by the Jurassic, it was drifting apart, its pieces slowly moving to become the continents we know today. Our world is just a snapshot of an ongoing journey, a single frame in a very, very long film. The Earth is breathing in and out on a timescale of eons. That single land was framed by a single ocean, Panthalassa, and the warm interior sea of the Tethys. These bodies of water shaped a world of climate extremes, a place of mega monsoons and arid interiors, a world both connected and divided. The very atoms in the ground beneath you were part of that world. The water in the clouds above was once part of that ancient ocean. There is an unbroken physical connection between that time and our own. In the rocks of that lost world, we find the quiet proof of its unity: fossils of the little reptile Mesosaurus, the hardy fern Glossopteris, and the resilient survivor Lystrosaurus are found on continents now separated by thousands of miles of ocean. They are the silent proof of lands once joined, a puzzle solved, not by myth, but by the patient work of science. They are the punctuation marks in a long and complex sentence. We have seen natural mysteries, like the eye of the Sahara, that look like the work of intelligent hands, but turn out to be the elegant artistry of geology itself, no less amazing for being understood. We have felt the ground shake with the memory of ancient cataclysms, the fire of the Siberian traps, the continental tearing of the Camp Volcanics, the cosmic collision of Chicxulub. These events remind us how quickly worlds can change and how thoroughly the slate can be wiped clean. They are the planet's great erasers. To date, no credible traces of a Pangean civilization have ever been found. The story of our planet, as written in stone, is one of natural processes. If a civilization like our own had existed, the Silurian, thought experiment tells us we would expect to find its signature, its chemical footprint, in the ancient layers. That signature has not appeared. The rocks are full of the stories of life, but empty of the stories of technology before our own. The myths of Atlantis, of Lemuria, and of Mu endure because they speak to something deep within us: our hopes for greatness, our fears of oblivion, and our longing for connection to a past grander than our own. They are powerful human stories, even if their settings are not geological realities. And so, science and story can coexist. One shows us, with care and precision, what is. The other allows us to explore, with freedom and imagination, what might be. The important thing is to keep them in a conversation, never to mistake one for the other. As you close your eyes, feel the slow, steady pulse of the earth beneath you. It is the same pulse that pushed continents together and pulled them apart. It is the rhythm of deep time. The earth is always breathing. Plates drift, seas open and close, mountains rise and fall away to dust. In all this constant silent motion, our own curiosity is the one constant. It is the light we use to trace the faint, ancient handwriting of time on stone. And now, it is time to rest. The story will keep going, because the world does.